So, luckily this thing stopped recording before I could overwhelm everyone. What I did in meantime, I'll calculate the algorithm for t is equal 3, and I basically found deltas for t4, which were maximized for j2, and then next step were again maximized for 2, and I found the new values of deltas, and then t is equal 5, which will be the last iteration. I found the new values of delta. For I1 it was maximized for j1, for I2 it was maximized for j2, and ultimately I put all of these values into our tables, and the tables look like this. So I did my best to calculate all of this, but obviously you see that's tedious. So at this moment, what I really did, I did the whole for loop here. I initialized these values, calculated these values, and calculated these values. And now what remains to be done is to do this step. So basically to find the most likely states. So I will first start this one. It says IT is argmax delta t of I, which essentially means what? In our case t is equal 6, so I'm looking at this column here, and I'm trying to see which delta is larger. This delta obtained for I equal 1, or this delta obtained for I equal 2. And I see that the first delta is 0.000 something, and this delta is 0.00. So this is approximately 1 order of magnitude larger than this. Therefore, this argmax will be equal to, because this value is larger than this value. Which means that the final state most likely is 2. And now I need to do the loop. This is the loop. For t goes from t minus 1 down to 1, look at this. Rt is pt plus 1 of it plus 1. What does it mean? It was 2. Now t goes from t minus 1 to 1. First starts t is equal 5. It will be I5, which will be P6 of I6. I6 is 2, so this is I6. So I5 is P6 of I6, right? And I6 is 2, so it's P6 of I2. Sorry, not I2, P6 of 2. P6 of 2 because I6 is 2. I6 is 2, right? So P6 of 2, P6 of 2 is 2. So the fifth state, most likely fifth state, was also 2. Now, go further. When t is equal 4, It will be I4 equal P5 of I5, which will be P5 of I5 is 2. P5 of 2 is also 2. So essentially I'm going this way, backward. Similarly, when t is equal 3, I3 will be equal P4 of I4. I4 was 2, so P4 of 2 was again 2. And you see how it goes. You have to look at 2 more. I'm sorry for using space like I'm using, but that's what I'm doing now. So basically I2 will be P3 of I3. I3 is 2. P3 of 2 is 1. So I2 will be 1. And I'm going this way now. Finally, I1 will be P2 of I2. I2 is 1. So it's P2 of 1. P2 of 1 is again 1. So I1 will be equal 1. And now what's my sequence? I1 is 1, I2 is 1, I3 is 2, I4 is 2, I5 is 2, I6 is 2. So most likely sequence is of course I1, I2, I3, I4, I5, I6. And now I will read what they are. I1 is 1, I2 is 1, and then 2, 2, 2, 2. So it's 1, 1, 2, 2, 2, 2. And now I can really answer how most likely this family traveled from Mexico to United States. In the first year and the second year, the family most likely was in Mexico, and then the last 4 years the family spent in the United States. This illustrated the Viterbi algorithm and also shown how it works. I will copy the algorithm once again so that we can analyze very briefly the complexity. So what are the inputs? The inputs are matrix A, B's, probabilities B's, probability pi's, and the output sequence. And the algorithm goes this is initialization, and then iteration. Remember, it starts from 1, not from 2. In fact, it should be also corrected in my notes. So this is the Viterbi algorithm. And now why I wrote this, first to summarize the algorithm, because otherwise it is scattered in the notes. And second reason is to basically be able to briefly estimate its time complexity. So basically this line is executed for each I from 1 to n. So the complexity is theta of n, right? Then, what we are doing here, we essentially need to calculate this product for each j being the state. So j can be 1, 2 to n. So I have n values to calculate. So that would be theta of n for each I. And I need to repeat that n times for all i's. So the complexity of these two without further ado will be theta of n squared. 1n coming from calculating the maximum, or the argument is the same. I can do these two simultaneously, right? And the second n coming from repeating that for each I. So this is theta of n squared for each t. So in each loop I have theta of n squared, and for all the loops, how many times I repeat that? I repeat that t minus 1 times. So totally this is theta of t n squared. T standing for t minus 1, but that's the same. T loops, and n squared standing for calculating maxima for each I. Now this one, I need to find the maximum. I goes from 1 to n, so this is again theta of n. And now this really repeats constant operation t minus 1 times, so this is theta of t. So the total complexity, time complexity, is what? Theta of n for initialization plus theta of t n squared for the iteration plus theta of n to calculate the most likely final state plus theta of t to calculate the most likely intermediary states. And when we calculate all of this, of course this is prevalent, so this is theta of t n squared. So algorithm is linear in the length of sequence and algorithm is also quadratic number of states. Actually, this is very good for two reasons. In real life, when the Viterbi algorithm is applied, it is really applied not of course to a case of a Mexican family, but it's applied in telecommunications where we need to decode among n symbols. The number of symbols in telecommunications is never very large, therefore n is typically small. So the fact that the algorithm is quadratic in the number of states, n, is not a big deal. What is really a big deal is the linearity of the algorithm in the length of sequence. Length of sequence, basically in telecommunication, may mean the length of a message. The messages can be long, but the good property is that the algorithm is still linear in the length of message. So it would allow relatively long messages, which is an advantage when we are dealing with telecommunications. So the time complexity is really good. What about space complexity? There are two sorts of things that we need to use in this algorithm. So I denoted them as a matrix delta and as a matrix P. Both matrices are, this goes for I and this goes for T. So both matrices are, since I can go from 1 to n and T can go from 1 to big T, both matrices are n times T. So the space complexity is certainly theta of n times T. This is again good. This is just linear in the length of sequence, and it's linear in the number of symbols. In fact, if you think more carefully, what we are doing, after we initialize these two for I equal 1, we use these two to calculate the next values. Then for the next values, for these values, we need just the previous values. We don't need these two values. So in fact, I can reduce the total amount of space I use to store the matrix delta, but nevertheless it won't influence the asymptotic complexity, the asymptotic space complexity. So dear students, this would complete the lecture on a Viterbi algorithm in hidden Markov chains. The Viterbi algorithm in hidden Markov chains is used to find the most likely sequence of symbols, in fact of transitions, that led to a given output. If you delve in more into Markov chains, you will find out there are other problems that can be related with Markov chains. One problem is evaluation problem. What is the evaluation problem? Evaluation problem means, okay, let's say we know the sequence O1, O2, OT, which is output sequence. So given is the output sequence. Goal is to find the probability this sequence is generated. I won't go into details of the solution for this problem, but you could guess it's actually similar to the solution that we have already shown. The second problem is estimation problem. The estimation problem actually asks to find most likely values of model parameters. Model parameters are matrix A, matrix B, matrix pi, given, observed, output. In the lecture notes I posted on Blackboard, you will find a solution of this problem. This is an interesting problem. I would advise graduate students to look at this. And the third problem is the one that we already seen, which is decoding problem. and which was find most likely sequence of states that led to the observed output. This would conclude my talk about Markov model. Before I really conclude this lecture, I will point to one more problem which is also resolved by dynamic programming, and this is so-called nucleotide string matching. So what is a nucleotide string matching? In biology, DNA is a sequence of 4 nucleotides which are denoted by A, G, C, and T. And of course they have wonderful scientific names which we won't bother in this class. And the problem is, say we have 2 sequences of nucleotides from possibly different organisms or even different species. Goal would be to optimally match these 2 sequences. Before we define what optimally means, say we are given these 2 strings. So it's one sequence could be AA, G, C, C, T, A, C. And the second sequence could be A, G, T, C, T, A, C, C. One possible matching could be this: A, G, C, C, T, A, C. And now pay attention. A, G, now space, T, C, T, A, C, C. So first we can observe that these 2 sequences, okay, they are in this case of the same length. The length, what would be the length? 1, 2, 3, 4, 5, 6, 7. A, G, C, C, T, A, C. And another one is, okay, I did wrong matching. A, G, T, C, T, A, C, C. So one sequence is of the length 1, 2, 3, 4, 5, 6, 7, 8. Another is of the length 1, 2, 3, 4, 5, 6, 7, 8. They are the same lengths actually, but I cannot 100% match these 2 sequences. So these 2 symbols match, and these 2 symbols match, and these 2 symbols match, but this pair of symbols and this pair of symbols don't match. Here I had to insert spaces, so these 2 are not matched with any symbol in this second sequence. And at the beginning and at the end, I also have unmatching symbols. So this is one possible way to match these two sequences. And I can evaluate how good or how bad the matching is. In order to do that, I need to specify a cost table. And I will write one possible cost table and explain the table. So again, don't forget, this was the sequence 1, this was the sequence 2. This is the cost table when I match different kinds of symbols. If I match symbols from first and from the second sequence, it costs me negatively. It's good. In fact, that's good. That's why the cost is negative. If I mismatch the symbols, say A with G, it costs me positively. So whenever two symbols are not matched with each other, the cost is +1, positive cost. And if I have to insert space, the cost would be even larger. So how I can calculate the cost of this? A and space cost me 2, A and A cost me -1, G and G cost me -1, C and space cost me 2, C and space cost me 2, T and T cost me -1, A and C cost me 1, C and T cost me 1, and then A, C, and C are matched with spaces, so each of them cost me 2. And when I calculate all of this, I will get cost. So this would be the cost of this matching, and naturally somebody can ask, what is the minimal cost? So how I will find it out? I will just illustrate the algorithm. And I know you are bored. I'm bored too, but I would love to do this because it really talks about one potential implementation of dynamic programming in emerging area, which is essentially bioinformatics. So let's do this algorithm. Let's show how this algorithm would work. First, I would put here symbol for space. And now we need to have the first sequence and the second sequence. So let's put here the first sequence, which is A, G, C, C, T, A, C. And let's put here the second sequence, which is A, G, T, C, T, A, C, C. So this is my nice big table. I will start populating this table gradually. So again, this was sequence 2, and this was sequence 1. So I will start filling this table the following way. I will put here 0, and then what is the assumption that I add symbol of one sequence and match with empty from another sequence. Whenever I do that, when matching a symbol from one sequence with empty with the space from another sequence, my cost will increase by 2. So I will start, and each time I reach a new symbol, my cost will increase by 2. Okay, there you see here. So I'm starting forgetting stuff. Similarly, what I could do, I can use space from the first sequence and adding spaces from the first sequence to the symbols of the second sequence, and my cost will increase by 2 this way. Good. So here comes the charm. Let's calculate what should be here. How I can reach this cell? There are 3 ways. This would be one way. This would be second way. This would be third way. If I go from this, and I will actually increase just that cell, so that we will see what we are doing. 0, 2, 2, space A, space A. So let's say we are going this way. This means start from here, insert A from first sequence, insert A from second sequence. A and A match. So the cost of matching A and A will be -1. Added to this cost, the total cost will be 0 plus -1, which is -1. Another possibility is doing this way. What this means? From second sequence, I won't take any symbol. Basically, I would insert space. From the first sequence, I would insert A. This means I'm matching space with A, which would cost me 2. Added to this old cost, that cost would be 4. Finally, and very similarly, I can go from here. From the first sequence, I am inserting space. From the second sequence, I'm inserting A. So I have matching of space with A, which is cost is 2, plus the old cost, which would be 2. So the total cost, if I go this way, would be 4. What is best? 4 or -1? Obviously, the best is -1, the smallest possible cost. So this is the optimal cost. In other words, to reach this cell, I would have cost -1, and the optimal way would be this way. So the cost is -1, and in order to reach that cell, I would go from that cell. Now I will start filling diagonally. Basically, I need to fill this one and this one. In order to reach this one, I can either go from 2 and match A and A. Matching A and A cost is -1. 2 minus 1 would be -1. Or this way, I would add 2 to the cost. Or this way, I would add 2 to the cost. So if I go this way, it would be 6. If I go this way, it would be 1. and if I go this way, it would be also 1. So I can decide either this way or this way. I can do this way. No, -1, yes. So the total cost would be 1 both ways. How about this guy? If I go that way, I would need to match 6G, oh this is now G, with I would need to match space with A with space, right? Which would increase cost to 8. If I go this way, it would be 4 plus matching A and G, which would be 5. If I go this way, it would be +1 plus insertion of space, which would be +3. So this is the most effective, gives 3. What about this guy? From here, in order to reach to this point, I can either go from here or from here or from here. The cheapest would be this way, because it increases the cost only by 2. What about here? If I go this way, the cost will increase by 2. If I go this way, by 1. If I go this way, by 2. So the best way would be to increase to 7. Similarly, if I go further, this would increase the cost by 2. This would be increasing cost by 1 because T and A won't match. And this would increase the cost by 2 because I'm inserting a space. So again, the best would be to increase by 2 this way. And again, the same thing. I mean, here I can also do this, because when A and A match, it would decrease this cost by 1 and will become 11. And here, this would be the most effective. So this way I calculated these arrows and these costs. Don't forget, this is +5, this is +3. Now I need to calculate the value here. In order to reach here, I can go from here or from here or from here. And in fact, the most cost effective would be this way. The total weight would be 1, because from here, from -1, I need to add 2 for insertion of a space to get +1. And then similarly, this would give 3. Now would be 5. Now would be 7. Now we can do this if we will. This, sorry, it's wrong. Why it is wrong? Because this would increase cost by 2 to 11, and the other way would increase by 1 to 13. And again, this would be the most cost effective. So this calculated these values, and now I need to calculate these values and these values. And after obviously very, very long and annoying calculations, I will try to copy what I got. So I will now stop and record the next video.